You are born with no language. You just know how to make some basic noises like ah, oo, ma, ba. Your mother teaches you how to combine those noises to speak the common language of your people. Hence the name Mother Tongue. Welcome to the world of data science, and I'm going to be your mother. On the cruel streets of data science town, you need to learn to speak the language of uncertainty. You need to know the slang of the data science gang, or they will destroy you. Why, if you don't speak their slang, they might even think that you are a poser, a mole from the software engineering gang who is just here to steal their fancy algorithms. The language is called probability. Probability is the language of uncertainty. There are three interpretations of probability. I'm going to focus on the most popular and conventional interpretation. Let's think about an experiment like tossing a coin or rolling a dice. The experiment is repeatable, but the outcome cannot be determined beforehand. These are called chance experiments. You can define certain outcomes of these experiments in words like the result of the coin toss is head, or the roll of the dice resulted in an even number. These outcomes are called events. For such chance events, we can talk about the probability of their occurrence. Imagine repeating the chance experiment an infinite number of times. Each attempt is called a trial. What is the relative frequency of an event occurring in those trials? Or what is the fraction of these trials in which the event occurred? If we denote the event by A, what do we mean when we say that P of A is P? That is, P of A is equal to P. For example, in the coin toss experiment, if A equals the result of the coin toss is head, what does it mean when we say P of A equals 0.5? A mathematician will tell you when we are talking about infinite trials, we are essentially talking about the limit. So in our lingo, P equals limit n tends to infinity, number of times event A occurred in n trials divided by n. Notice that this number is between 0 and 1. Let's get back to the coin toss experiment. Mathematically, I can define a variable to indicate whether a trial I resulted in a heads. xi equals 1 if the ith trial resulted in heads, 0 otherwise. After conducting the experiment n times and taking the note of the outcome in each trial, I can define my estimate of p as p hat. And p hat equals summation I equals 1 to n xi by n. When I say that the probability of heads is 0.5, what I mean is that as n tends to infinity, p hat tends to 0.5. So let's say the first trial results in a tails, which I denote by 0, second results in head, which I denote by 1, third results in heads again, fourth in tails, fifth in tails, sixth in heads, and so on and so forth. Then if I add up all of these numbers and then divide by n, as n gets larger and larger, this number will get closer and closer to 0.5 and eventually converge to 0.5. This interpretation is called the frequentist interpretation of probability. There are two other interpretations called the subjective interpretation and the logical interpretation. I'm not going to go into the details of these interpretations because the rest of the data science saga is based on the frequentist interpretation. The data science work that you will eventually end up doing in the real world is also based on the frequentist interpretation. However, if you have a curious mindset, you should check out the meaning of those interpretations as well. Now comes the terminology. That means you gotta remember these names. They are the code names that you will use while talking to other data scientists about our illegal chance experiments. Keep these names a secret. The set of all possible outcomes in a chance experiment is called the sample space. We are going to denote this by the big omega. Now, some of you guys may be scared of Greek and Latin, but you know what? There is an ancient Indian saying that dar ke aage jeet hai. In English, it means beyond fear lies victory. So if you want to learn this subject well, you will have to overcome that fear of Greek and Latin. Back to the sample space. So, for example, if your chance experiment is tossing the coin once, the sample space is H and T. H stands for heads, T stands for tails. If your chance experiment is rolling the dice once, the sample space is the set of 1, 2, 3, 4, 5, and 6. If you are drawing one card from a deck, the sample space is the set of 52 cards. Or maybe 53, if you are serious. Yeah, get the reference? Yeah, if you include the joker, yeah, you get it. The above examples are that of discrete spaces. But think about observing a light bulb, and your experiment is observing the lifetime of the light bulb. That is, how long it lasts. Now, we are not certain when the light bulb will burn out. It depends on the quality. However, we can guess that as we go further and further in the number line, the chance of observing that long a lifetime diminishes. There may be some rare high quality bulb that might last really long. Who knows? It is an example of continuous sample space. The sample space would be 0 to infinity, or the set of all positive real numbers, since the lifetime cannot be negative. Mathematicians denote the set of all real numbers by capital R. Since we are only looking at the positive side, it is denoted by R+. So what is an event? It is a statement in the common language about some feature of the outcome of a chance experiment. But more formally, an event is a subset of the sample space. For example, if your experiment is rolling the dice once, you might define an event as the face is an even number. So A equals a set of 2, 4, 6, which is a subset of the sample space 1, 2, 3, 4, 5, 6. Or if the experiment is rolling the dice twice, the sample space is the set of 1, 1, 1, 2, 1, 3, and so on. The pairs of 2 till you get 6, 5, 6, 6. So this means the first roll was a 1, then the second roll was also a 1. First roll was a 1, second roll was a 2, and so on and so forth. You can write down all 36 elements if you please. And the event is the sum of the two rolls is 4. So A equals 1, 3, 2, 2, and 3, 1, which is a subset of omega. I'm going to introduce the term script A to denote all the possible subsets of a sample space. That is, the collection of all possible events. For example, in a coin toss experiment, script A is H, T, and HT. In the dice rolling experiment, script A is 1, 2, 3, 4, 5, 6, then 1, 2, 1, 3, so on and so forth, all sets of 2, then the sets of 3, 1, 2, 3, 1, 2, 4, and finally sets of 5, 1, 2, 3, 4, 5, and 2, 3, 4, 5, 6, and finally 1, 2, 3, 4, 5, and 6. You could express each of these subsets of script A in words, that is, as events. For example, this 1 can be expressed as the roll resulted in a 1. Now, what is probability? Actually, probability is a function. I bet you did not think of it that way, but it is actually a function. Let's write it like this. So if it is a function, it must have an input and it must produce some output. In mathematics, you might have seen functions being represented as f of x equals y. It has a domain, that is, the set of legitimate values for input x that this function can process, and a range, that is, the value of y that the function is capable of producing. For any chance experiment, the domain of the probability function is script A, and the range is real numbers. So in the mathematical representation, P is a function from script A to R. Now, probability cannot output any arbitrary real number. It is bounded by 0 and 1. So it only maps events to numbers between 0 and 1. So can any function f that takes in an input and produces a number between 0 and 1 be called a probability? No. The definition of probability is as such. Probability P is a function from script A to R such that, number 1, P of omega equals 1. That is, if I provide the entire sample space, it covers all possible events and therefore the output must be 1. Number 2, P of A is greater than or equal to 0 for all A, which is an element of script A, which basically means every element has a positive probability. Negative probability is not allowed. 0 probability is okay. Number 3, if any two events A and B are mutually exclusive. So if events A and B are disjoint sets, they have no common elements, then P of A union B equals P of A plus P of B. This is the definition of probability. Great, now you know the formal definition of probability. Remember that script A is tied to your chance experiment. So different experiments have different events and the output of the probability function will change based on the elements of script A. Now, how do you actually calculate the probability of a particular event in the sample space? Now, one method is called the classical method of calculating probability. It is used when your sample space is finite. The assumption in these methods is that all possible outcomes in the sample space are equally likely. For example, in the coin tossing experiment, omega is ht. Both heads and tail are equally likely, which means P of h equals P of t equals 0.5. In the dice rolling experiment, omega is 1, 2, 3, 4, 5, 6. Each of these faces are equally likely, that is, their probability is 1 by 6. Under these assumptions, the probability of event E is defined as P of E equals the number of outcomes favorable to event E divided by the number of possible outcomes. Remember this definition because you will need it to continue our saga. I'm going to teach you the various ways in which you can compute the numerator and the denominator of the above equation. I hope you liked the journey so far. If you want to continue the journey, you must subscribe and like. Some smart mathematicians have found some simple rules that you can use to count in these complicated cases. Let me introduce you to the fundamental counting principle.